Hi, welcome to EE16B. My name is Sid, he's Savan, and for the record, I'm taller than him.
I'm actually 6'6", but in any case, let's get started. Today we're going to do a practice midterm problem. We have a RLC circuit that we're going to derive the transfer function for, and then plot the Bode plot, and then note interesting features about all of them. If you notice that this is a second order circuit, we note this because there is both an L and a C in it. So this means that we might have some sort of harmonics or some sort of different or interesting behavior. We will talk about that later. Anyways, so to get started, the first thing that we want to do is we want to derive a transfer function. We have to move this circuit over to the phasor domain, into the phasors. So to do that, we note all of these circuit elements as respective representations in the phasor domain. All right, Sid, what is a capacitor in the phasor domain?
I wonder. Is it 1 over I omega C?
That's correct. Inductor?
Yay. Wait, before that, 10 points to Gryffindor. Right? Okay, inductor is I omega L.
Great. And then resistor stays the same, right?
Yeah.
Resistor does not have any frequency dependence, so we don't mess with it at all in the phasor domain. All right. So we have these. From here, we're going to put together the KCL and KVL equations and then solve V out in terms of V in. All right. So the first thing that we can note is that there's one major node at the V out terminal. We know it's one node instead of twos because they're all connected by wires and there's no circuit elements in between. Okay. So doing that, we're first going to start labeling currents. Let's call this going outwards I1, this is I2, and this is I3. Great. So now that we have that, we note that they're all coming out of the same node because they're all connected by wires. And we can say that I1 plus I2 plus I3 equals 0. And then we know that I1 is just V out minus V in over 1 over j omega c. This is just the impedance of this element, of this first element. I2 is V out over the impedance of the inductor, which is just j omega L. And then I3 is just V out over R. Great. So now we have V out and V in terms of each other. And well, all we have to do is solve for V out in terms of V in, which is a pretty tractable problem, wouldn't you say? Just algebra. Okay, so first let's move V in to one side and V out to the other. So rearranging, we have V out times j omega c plus V out over j omega L plus V out over R equals V in times j omega c. I apologize, my C's kind of look like L's. I'll be better about this. So from here, we know the transfer function h of omega is V out over V in. And moving around, we have j omega c over j omega c plus 1 over j omega L plus 1 over R. And then multiplying through by j omega L so that we have polynomials on the top and the bottom. We have j omega squared LC over j omega LC, j omega squared plus j omega L over R plus 1. Great. We've solved for our transfer function in the standard form.
Cool, and I will continue in the next video. We have switched positions. Cool. Okay, so From the last slide, we got that our transfer function is this thing. And now we're going to try and draw its Bode plot. Specifically in this slide, we're going to try and draw its magnitude Bode plot. So we're only going to consider ourselves with this column right here. Cool. So if you're drawing a Bode plot, we obviously need values. So we've provided some here that conveniently work out for the range of numbers that we've given here and here. So L is 1 millihenry, C is 1 millifarad, and R is 10 kilo ohms.
Just as a reminder, milli is 10 to the negative 3 and kilo is 10 to the third.
Cool. So the first thing we're going to try and do when trying to make this Bode plot is to look at this term down here. You can look at the numerator first, it doesn't matter, but we're going to start with the denominator. So we're going to try and pattern match this term to something over here, to something in this region. So looking at it, this is kind of like 1 over I omega squared over LC plus, LC plus something. So this kind of looks like a quadratic pole, which is where like the whole n is equal to 1. So we're going to pattern match, if I can erase all this, we're going to pattern match this to a quadratic pole, where n, this n over here, is 1. Cool. So the first thing we're going to try and do when pattern matching these things is to look at this term. This, I'm going to erase this so I can highlight this better. I'm going to look at this term, and I'm going to compare it to this term. Because the first thing we're going to try and do is determine the cutoff frequency. And this cutoff frequency that we determine is only the cutoff frequency for this term, because one of the main aims of a Bode plot is to segment the terms into different components and then treat each component separately, which is why the Bode plot abstraction is powerful. So trying to find omega c, we can pattern match these two, and we get that, I'm sorry if I write a little bit, but we have j omega squared times LC from here is equal to this term over here, which is j omega squared divided by omega c, the whole squared. So these two terms cancel, and we get omega c squared is equal to 1 over LC, which tells us that omega c is equal to 1 over square root of LC. Cool. So just as a reminder, as I erase, just as a reminder, this cutoff frequency at omega c is only for this denominator term, as we're segmenting it, as I mentioned earlier. So, pattern matching this to this, we see that the magnitude plot sort of goes at 0 dB until it hits omega c, and then it starts decreasing.
Hey Sid, what about the linear term?
Oh, that's a great question, Saban. He's talking about this small, I don't even know what Greek alphabet this is, because I keep forgetting, but we're going to call it nervous Greek alphabet. So this psi term is not really relevant while we're constructing a Bode plot, because as you can see, this whole thing and this whole thing, like these two, don't involve the psi term. And this is why Bode plots are a useful approximation of the transfer function, and it's not an accurate representation of the function itself. But the reason why we ignore it is because for high frequencies, this term is going to dominate over this term, so we just like set this to 0 because we're electrical engineers.
Is it just for high frequencies, or it's for all frequencies, right? Or for any frequency that's not around the cutoff frequency? That's a pretty good approximation.
Yeah. I'll trust him on this. He's the most circus person among the two of us. Cool. Okay, moving on. We've got that for this term, omega c is equal to 1 over square root of LC. This is 10 to the minus 3. This is 10 to the minus 3. Square root of this product is square root of 1 to the 10 to the minus 3 squared, which is 1 over 10 to the minus 3, which is equal to 10 to the 3. Cool. So erasing all that, bye-bye. This is equal to 10 to the 3. So this term, when you actually plot it, would be 10 to the 3. So putting this away, we're going to be fancy, choose a different color. I don't know what to choose, purple, cool. So this whole thing is going to be 0 until 10 to the 3, which is cutoff point, and then starts decreasing at 40 dB per decade. So there you go. Whoops. So that's our magnitude Bode plot for this term. Now we're going to look at the numerator. But the way it's presented is kind of like we're trying to get here. So changing back to colors for a second, going to red. This LC term corresponds to this constant, and this, oh, well, dang it. Okay, let me just try to make the color thing work. Okay, so this term corresponds to this thing, where n is equal to 2. So in this case, we tried and pattern matched. We tried to pattern match LC to the omega c over here, to the omega c in a quadratic pole. But in this case, this literally consists of 2 separate terms. Cool. So we're first going to consider the green one. So, whoops. We're first going to consider this term, the 0 at origin. So this, as you can see, crosses 1 at 0 dB, and then it just goes, previously it goes to infinity at negative 20 dB, and ahead it just goes at plus 20 n dB per decade, and for our case n is equal to 2, so this whole thing is 40 dB per decade. Cool. So plotting that.
Just have a line going up from 0 at 40 dB per decade, right?
Yeah. So
or 10 to the 0.
This is 1 as a reminder. So we have 1 here, then it goes up at 40 dB a decade, and goes back down at 40 dB per decade. Cool. Now we're going to try and do the constant term. So the Joker from Batman is green, purple, and
red.
Red?
Red.
No, he's not red. Is it? No, it's like he has white makeup, but we can't use white. We're gonna work in we're gonna create a new Joker that, well, actually red for all the blood he spills. That's extremely morbid, I'm sorry. Okay, so LC. So if you didn't get the Joker joke, congratulations, you're not a comic geek. Cool. If you did get the Joker joke, congratulations, you're awesome. I approve. Regardless, you're awesome. Okay, so as you remember, this is the constant term, so constant k. So we're going to try and find 20 log k. So we're going to look 20 times log of LC. So this times this, which is 10 to the minus 3, times 10 to the minus 3, which is 10 to the minus 6. So it's 20 log 10 times 10 to the minus 6, which is equal to minus 120. Cool. So you know that that's at negative 120. Oops, I didn't mean to erase that one. Change colors. You know what? Just let's erase it. Forget it. It's not important anymore. So we're going to draw a constant term at negative 120. Cool. So, go away, PowerPoint.
Now what do we do? Yeah,
now what do we do? So, one of the main advantages of using a Bode plot is that products become sums in log scale. So we have these individual functions in log scale, and these individual functions as products. So in log scale, the result is just adding them together. So we just need to add this plot to this plot to this plot to get the resulting Bode plot. Cool. So, excuse me. So let's change colors again to yellow. I wonder if you can see yellow. Let me go orange. So, cool. So this is sort of like your baseline, which you're just going to consider as your starting point. And as you can see here, you're going down at -40, so we add that to this. And then here you keep increasing, whoops. And now it keeps going up, so we go at 40. We go at 40 all the way to the top until we reach this point where we start increasing the same rate at which we start decreasing. So from here, it becomes a baseline too. It becomes flat. So that's our magnitude Bode plot from here to here. Ta-da!
Great. So what happens with the linear term? We kind of just ignored it before, right?
Yeah, why don't you tell me? I'll give you the pen.
Well, so the linear term, it only really matters when omega is approximately equal to omega c. That's when the linear term matters most, and that's when it plays the most importance. So what happens here? I mean, let's think about this, right? So you have this term, and we've called it in lecture, we've called it the damping term. Why do we call it that? Well, why this is an approximation is that we have a sort of resonance at the cutoff frequency. What's happening is that the capacitor and the inductor in the original circuit are in phase with each other, and they're causing distortions. So what actually might happen if we have large R is going to be our yellow curve. So what about, say, medium R? So that means that there's a little bit less damping. Let's draw that in black. So in that, everything up until the cutoff point is the same, but we're going to start noticing some weird things, like a bump. Great, so this is medium R. Now, what happens if we get rid of the damping entirely? What happens if we get rid of all of the resistance in our circuit? Well, then this middle term goes to infinity, doesn't it? Because R goes to 0 and it blows up. Well, what ends up happening is that just like our that term going to infinity at the cutoff, this purple goes to infinity at the cutoff frequency. And another thing to note, and this is R equal to 0. So this happens always at the cutoff frequency. Another thing is that as we increase our damping, so when we go from 0 to medium to large, this peak becomes less sharp. So this damping sort of spreads out a little bit more, and it can lead to useful behavior when we talk about bandpass and bandstop filters. But that's just a small sort of excursion into why we care about these damping factors and what this linear term really means. But moving on, let's look at the phase plot.
Cool.
I get to snap this time. All right.
Someone has risen.
I have. We're now going to do the phase plot. So as we did before with the magnitude plot, we're going to break up the transfer function into its constituent parts and then treat each of them individually. So same as before, let's look at the denominator. So the denominator is a quadratic pole, and the phase of the quadratic pole just stays at 0 until 1/10 of the cutoff frequency, and then rises to -180 times n at 10 times the cutoff frequency. So here, n equals 1, as we saw before, and the cutoff frequency is 10 to the third. Cool. So drawing that part, we start off at 0, and then 1/10 of the cutoff frequency is 10 to the 2, so we drop. And then at the cutoff frequency, we should be at -90 degrees, moving down further.
Cool.
And then we flatten out.
Salvin, is there a difference between -180 and +180?
There's no difference between -180 and +180. So I could have equivalently shifted this graph up by 360 degrees and had this start off at 360 and then drop to 180 degrees.
Yep.
Would have functioned the same way.
Cool.
Okay, so now that we have the quadratic pole, let's look at the pole at the 0 at the origin.
Keeping with the comic book theme, let's do it in blue color. This time let's try and do Spider-Man, which is significantly less morbid.
Or Superman.
Oh, Superman.
Great.
He's too... He has no weakness, which is why I don't like him as much, but whatever.
Anyways.
Not relevant.
So looking at the 0 at the origin, here n equals to 2. So it actually stays, a 0 at the origin causes 2 times 90, 180 degrees offset.
Mm-hmm.
So we actually just have this.
We could have equivalently drawn it at negative 180 because it's the same thing.
Yeah. So you can shift this by 360 degrees in any direction, and it'll still be the same graph. Okay. So finally, adding them together, any color preference?
Black.
Black.
Because when you draw Spider-Man, the webbings are black. Because we usually can't draw white.
Okay, so here we start off at 180.
Cool.
And then because of the quadratic pole, we're going to start dropping. And we're going to hit 90 at the cutoff frequency.
Mm-hmm.
Keep dropping.
Mm-hmm.
And flatten out again.
Cool.
Okay, so this is the Bode approximation, right?
Mm-hmm.
And as we had talked about with the magnitude plot, this isn't entirely accurate. And we basically ignored, again, this linear term.
Mm-hmm.
So how does this linear term, this damping term, affect it? Well, it actually affects the sharpness of this drop. So we approximated it as a drop over 2 decades, but in reality, that's not entirely the case. So we did the case for R is large. How about the case where R is the middle? So for medium R, it actually starts dropping faster. So it might look something like, this is poorly drawn, but it still goes through 90 at,
I see.
still goes through 90 at the cutoff frequency,
Mm-hmm.
but it just does so sharper. Okay, what about, again, no damping, or just a really small damping factor? In that case, it's a really sharp transition, so it looks almost flat up until the cutoff.
I see.
So the major point here is that at the cutoff frequency, it always hits 90 degrees or minus 90 degrees. And then what it does is dependent on how much it's dampened. And this is just an important part of how quadratic poles function.
Cool.
And with that, we've drawn the magnitude and the phase plot, and we're done.
Awesome. Good luck.